was pretty smooth through the whole, I mean, I guess I was on the other side.
Seemed like well, I can actually point to the screen, but I don't know. I don't even need that. Okay. All right.
Well, so,
And then this is substantial. And then this one's right arrow. Let's go here. Volume.
Exactly. The proposal's solid. We're not here to talk about.
I can see. And I don't know. Okay, and then right arrow, left arrow for fence. All right.
That was the image on that one.
Yeah, it's fine. I'll just
There's.
I'll figure it out.
Yeah, this is all fine. We're just gonna have fun here. Great. Yeah.
All right.
Holy crap. Oh, we get.
I think we're gonna get started, y'all. Well, good morning, everyone, and welcome to the spring quarter School of Aquatic and Fishery Sciences quantitative seminar. This is our first quantitative seminar, so thank you all for being present. For those of you in person and on Zoom. I'd first like to begin with the land acknowledgement. The University of Washington acknowledges the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. I'd like to introduce today's speaker, Dr. Matt Falcy, who is an assistant unit leader of the USGS Idaho Cooperative Fish and Wildlife Research Unit and assistant professor of biometrics in the Department of Fish and Wildlife Sciences at the University of Idaho. He works on fish and wildlife problems that emphasize modeling. Using Bayesian statistics, math, and numerical simulations, Matt's research seeks to project population dynamics under future conditions. He is also interested in optimizing human decision-making around management objectives and measures of scientific evidence. Matt teaches graduate courses on ecological modeling and Bayesian analysis in ecology at the University of Idaho. Matt's previous positions include working for the Oregon Department of Fish and Wildlife, where he developed salmonid population models and decision support tools. He received his PhD in evolutionary biology with a minor in statistics from Iowa State University. Please help in giving me a warm welcome to Dr. Matt Falcy.
Well, thank you all for the invitation. I like the small group. Hopefully we can make it intimate by having you all just chime in at any point as I'm going along. If there's a question or comment, by all means, please do so. Speak up. I will certainly not speak for more than 50 minutes, so there's going to be a lot of time, so don't worry about derailing me here. So I would like you to think of an example in fisheries management where uncertainty is used explicitly in a decision. Okay, but let me clarify what I mean by used explicitly. There's two words there, and there's kind of two definitions I want to get across. To use uncertainty would mean that different levels of uncertainty would result in different decisions. And to use this uncertainty explicitly, what I mean is that the way in which uncertainty maps into different decisions is transparent and repeatable, and it can survive outside of someone's mind. So this is usually some sort of transcript, a diagram, code, or math, okay? So with those definitions in place, think of an example in fisheries management where uncertainty is used explicitly in a decision.
Well, the P-star rule in the US West Coast, where the more uncertainty there is, the more you reduce the catches.
Yeah. That is one of the yeah, and Sarah Converse is here, so Professor Converse will probably already have a long list of these. But it's funny you mentioned that one because it's one of the first ones that I became aware of. I was like, oh wow, there it is. And I have since been keeping a little tally of these examples, and my tally is not very long. And as I presented this, I'm presuming, particularly for the grad students who've just simply had less time in the profession than the rest of us, your list might be zero. And so this is problematic in the sense that we do spend a lot of time thinking about how to quantify uncertainty. But why, if it is indeed difficult to think of examples where we're going to use this uncertainty in a way that actually matters? Okay, so addressing this problem is one of the themes of my research. All of my graduate students work on real problems in the real world, and so did I when I worked for the Oregon Department of Fish and Wildlife for 10 years. But when I get my own time to think, I like to step out of that and think about the conduct of our science a little bit more philosophically and abstractly. And so the story of the ecology of uncertainty is told with 26 equations and 0 pictures of nature. But I can promise you this. I will show you ideas that transcend particular locations, times, and taxa. And I'll show you ways of using standard scientific uncertainty and blending it with human values in a mathematically rigorous framework. So in fisheries or even fish and wildlife and many applied domains, we have essentially 2 non-overlapping magisteria, that of science and that of people who could be affected by the science and the decision making. There is a little bit of overlap between the two, and this is really where decisions happen. But many of you may be aware of the difficulty in translating science into action. And the reason for this is simply that p-values are not decision criteria. Okay, they cannot be a decision criteria for any decision that actually matters because p-values have nothing to do with human values. So just as a reminder, p-values decline with sample size when the null hypothesis is false. And the null hypothesis is almost always false in anything ecological simply because of the extreme complexity or the number of connections of things that do occur, even if it's not a strong effect. And this reality of the statistics has been pointed out many times, including in this provocatively titled paper by Douglas Johnson, The Insignificance of Statistical Significance Testing. And this came out approximately a quarter of a century ago. So this is obviously nothing new. Johnson, in his figure 2, comically reinterprets p-values in terms of the sample size and what the researcher wishes that they could say about about reality. And in the subsequent, 2 decades, in the 2000s and into the 2010s, there was a lot of debate and controversy surrounding the use of p-values in science, including the American Psychological Association proposing an outright ban of p-values from all of their journals. And this debate certainly occurred in ecology as well. There also occurred a fair bit of clarification on what p-values intend to measure and what their usefulness is. To me, as somebody who's concerned about real-world applications, all of that debate is extremely pedantic, to the point of being almost besides the point. Like, it just does not matter for the things that I care about, which is taking scientific evidence and converting it into decisions. But you also may be aware that this gap between publications and public actions is something that exists in our literature and is something that we are actively trying to close this gap. And one of the ways that this is happening is through human dimensions research. And so you can see through this really simple, this took me 2 minutes to do this Google Trend search for for human dimensions research. It's just spiking, right? And I think this is wonderful. But to be more precise, I think that this is necessary, but it is not sufficient. And so I'm going to show you what sufficiency looks like as this moves along. It is not sufficient because human dimensions alone, in my opinion, at its best, will quantify utility of how people reap benefit from actions in the real world. But if we blend that with applied ecology, in particular Bayesian analysis, for reasons I won't get into, it's nice, but not required. If we put those two things together, we land at decision theory. And there's some really neat things we can do when we marry these two otherwise disparate and unoverlapping magisteria. All right, so that's the context for what I want to present, which are essentially 2 papers. The first one I recently published, and it's going to essentially be about how to quantify uncertainty in a particular scenario, and then how to use it as well in a decision. And then in the second paper I'm going to present, which is under review, it's much more abstract and mathematical about how to integrate statistical evidence in people's values, right? That was the promise I made to you. That's going to come at the end. Okay, so the first paper just came out recently in the North American Journal titled Refining Indices of Risk from Salmonid Hatcheries. So this story begins with natural selection. So at the top panel here, we have a group of individuals in a breeding population that all have a different phenotype. And their mean phenotype in this hypothetical example is 0. But they have a standard deviation of 1. But not all of these individuals have equal likelihood of surviving. That survival function is given in the middle panel, and you can see that the optimal phenotype is 1. So it's not actually what the population's average is. It's just a little bit different. And so when you run these individuals through this selective sieve, you get out a population with a different mean. And in fact, we started off with a mean of 0, and after selection, we get a mean of 0.5. So I ran this with a really simple simulation, but the math for this has been known for 50 years. The question that becomes more interesting and perhaps all relevant to some people here, particularly those interested in salmonids and the hatchery management of salmonids, concerns what happens when we have different selective pressures operating in the same population. Right? So if you're born in a hatchery versus being born in a river, there's different optimal phenotypes. And so what happens in the long term when both selective forces are at play? It is not the case that one individual would experience both environments, but across generations, the population does experience both selective forces. Well, this is let me first just explain and define pHOS, because many of you probably know that, but we have here the two different selective regimes at play. So some fish are born in a hatchery, and then they come back into the hatchery and being used for broodstock. But some of them that don't return go and breed in the wild. They escape and breed in nature with other potentially natural origin individuals. And so this proportion of hatchery origin spawners, pHOS, is an index of interbreeding from individuals from the hatchery that breed in the wild. But we also have individuals that are born in the wild and can be taken back into the hatchery and used as broodstock. This is the proportion of natural origin broodstock, pNOB. Okay, so some definitions to make sure you get straight, because the first half of this talk won't make much sense if you can't keep pHOS straight. Okay, proportion of hatchery origin spawners. Okay, so Michael Ford, about 24 years ago, worked out the math for the long-term phenotype that would emerge in this situation of interbreeding when there are different optima in nature and in the hatchery. And then you can simply plug this equilibrium phenotype into this equation, and you get back out the long-term fitness of the entire collective population. What I want to draw your attention to here is that these proportions, pH and PW, they're fixed, right? In this equation, it's just a number, right? Which would imply that there's just this long-term constant proportion of interbreeding, right? So it's essentially like panixia of across generations, all individuals just interbreeding with a fixed proportion that never changes. Okay, so we can take this math that Michael Ford worked out and plug it into a computer and plot what happens to fitness as a function of pNOB, which is under human control, right? Because we take these fish out of from that were born in the wild, and we take them into a hatchery. We can breed them in there. We can control pNOB. We can partially control pHOS as well. It's a little bit harder. Details matter. but I'll just point out that pHOS is partially controllable. And so when you look at these rates of interbreeding, you can just plot out the math here that Michael Ford developed. And these colors are indicating the relative fitness of the population. And so when pNOB is low and pHOS is high, we have relatively low fitness, right? Because this is the effect of domestication selection, right? These are the dogs breeding with the wolves, so to speak. And we can also look at, well, what happens when pHOS is low and pNOB is high, and we get relatively higher fitness here. Okay, so there's this concept in salmon management of PNI, proportionate natural influence, which is simply pNOB divided by pNOB and pHOS, right? And that's what's being shown in these black isobars here. And notice how nicely those black isobars map right into the colors, the color isolines as well. And that you've got this lower region here where you've got relatively high fitness. So this is what led Craig Busack to coin this term, the golden triangle of genetic goodness. This is probably 20 years ago that this happened. And they came up with this management recommendation that PNI should be above 0.5. And this has dictated how hatcheries are managed in the Pacific Northwest for about 20 years, ever since hatchery reform began through the HSRG. And in fact, to my understanding, Washington Department of Fish and Wildlife was mandated to follow the recommendations of the Hatchery Science Review Group until I think about 6 or 7 years ago. So it's a big deal. You notice at the top there, this is a scenario of weak selection. These are Michael Ford's default settings in his 2002 paper. But look at what happens if you look at a scenario of strong selection. All of that fitness space, which currently occupy the lower right-hand triangle, just gets smashed down into this much smaller sliver over here, suggesting that the strength of selection is important. And in 2002, when this work was originally done, I think most people thought that the strength of selection is not super high, but then there's been a number of genomic discoveries that make us realize that it can occur pretty quickly. And with just a single nucleotide change, you can get a whole different run timing, for example. So this potential for strong selection is something that we need to be thinking about. So this all leads to getting back to, so I'm going to come back to this idea of the strength of selection, but we're just going to move on for a second here. The standard way that folks would calculate and index this risk of domestication selection was by calculating pHOS like this, right? You've got some population, you know how many of them are hatchery and how many are wild. You add up all the hatcheries and you divide by the total, bam, that's pHOS. Okay. The problem is that nature is usually not panamictic. It instead has segregated breeding in space and or time. So here, this I, and you'll see it later, so I is space, but it works exactly the same in time. There are different run timings between hatchery and natural origin fish. So we can consider space and time. Here I'm just showing for simplicity, two spatial units. But if you think about what's going on in this case, which I would argue, maybe this is a bit extreme, but that is also extreme on the left. But if you think about this, the rate of interbreeding of hatchery origin fish with natural origin fish is really low over here. Over there, it's a 50-50, like probability of hatchery and natural origin breeding. Over here, it's extremely low, right? We've got two hatchery origin fish breeding with a bunch of natural origin fish over here. And then over here, it's a bunch of hatchery origin fish with two natural origin fish, right? So the problem is when people use this simple math on the left and apply it to this situation here. This is not the same rates of interbreeding that is in that Ford equation I showed you, which motivated the whole use of pHOS as an index of risk from domestication selection for 20 years under the ESA. So let that sink in, right? Like it was essentially, in what I'm saying in this paper, and you can tell me that I'm wrong, and but it's already out, is that it's been calculated wrong for most realistic situations. It's been calculated incorrectly. So what we want to do to get a metric that is commensurate with Ford model and thus an index of risk from domestication selection is we get our typical pHOS here for each one of these units, and then we just simply weight it by the number of natural origin fish, W for wild, but it's more proper to speak of natural origin because nothing is truly wild. But W and natural origin are the same thing, and I'll probably switch back and forth. But so we have these natural origin fish, and so we just want to weight these two different measures of pHOS by the proportion of natural origin fish in the entire population. Okay, that's the proposal that is a fix to this. So here's just a very simple junior high math kind of example of how this works. You've got these two different sites with hatchery and natural origin fish. Sum up some stuff, and you can get these two different pHOSs at these two different locations. What most people would do is they just look at, well, how many total hatchery fish and how many total natural origin fish do we have? And they arrive at this calculation of pHOS, 0.36 or 0.37. Right? But what I'm proposing you do is that you weight these two individual pHOSs by the proportion of natural origin fish in each of the two subgroups, and you get a number that is not the same. And it's actually quite a bit lower. So this is the basis of my claim that pHOS has been overestimated. Come back in the end, like it's always just an index of risk anyway. This is not an absolute measure, it's an index, but the details of how this works do in fact matter. Yeah.
Question is, if the proportions were the other way around, so the big side had a higher proportion and the small side had a lower proportion, would the result be the other way around?
No, it would not. And in fact, this next figure is going to get at that. Yes, well, you know what, maybe I don't fully understand the question, but if the proportions had simply like as I know that you would get this, that like the location of it doesn't matter. So if the proportions were the other way around, I think we wind up in, if we just simply did this, we get the exact same number, right? Yeah, so in this case, it wouldn't matter, like the location of like if the left-hand side and the right-hand side doesn't make any difference. Oh wait, no, I'm sorry. Yeah, because it would be this times this plus this times this. So it would be a different number, excuse me, yeah. But where I think the take home here is that the traditional pHOS metric is always greater than the weighted one. There is the only scenario in which they are identical is under that assumption of perfect panmixia, right? Otherwise, you're always multiplying this proportion by a little weight, and so it's always going to be less. So here I've just taken 1,000 fish and I've partitioned them across 5 locations and 2 origin types, right? So there's essentially 10 different groups here. And I use this Dirichlet distribution just to do this randomly with equal probabilities across all of these 10 bins. And then I calculate the traditional pHOS on the x-axis, and then the proposed pHOS on the y-axis. And so you can see that every single one of these results in pHOS, a weighted pHOS, which is lower than the traditional metric, the naive metric of pHOS. Okay, so this is again the claim that the metric pHOS has been overestimated. It doesn't have to stop there. We know that there are age and sex specific differences in the fecundity. So why treat all fish equally when we know some females are bringing back way more eggs than other females? So we can wrap in the fecundities of different types of fish as well, and further weight the pHOS by these types of fish. So in the upper left-hand corner, we've got 6 different ages of fish, and then their fecundities by age and sex. And so like in this case, a small female a young female doesn't contribute a whole bunch, but a small male doesn't contribute a whole bunch, but the female does. But then as they get older, they start to equalize, right? This is completely made up. It wouldn't be hard to go into a hatchery and just look at how many eggs the different aged fish have. The milt is probably not too hard either, for that matter. So anyway, if this information is known, you know something about the size structure of your population, it can be brought in to this calculation as well. And I'll point out that if you don't do this, you fail to acknowledge this, that is exactly identical to assuming this table is full of ones. So it doesn't go away because you ignore it. You just tacitly assume equality if you just tally up all these fish without weighting them. Okay, so uncertainty doesn't go away just because you bury your head in the sand. All right, so now we're getting to some of the good stuff here. All of that was just developing the proposed change to pHOS calculations, but there has never been in the 20 years of its use any estimate of the uncertainty. No standard estimators for uncertainty. So I worked on that. So there's different kinds of uncertainty that we can have here. If we go to a specific site and location and we count fish, we take fish and we look at their origin type by whether they have an adipose fin clip or not, is the typical way. We have no uncertainty about the proportion if you sample all of the fish in a particular place and time. But if you get a subsample, now there's uncertainty due to sampling, right? So this is the hypergeometric distribution. This applies sampling balls from an urn without replacement, right? So you take them out. If you sample all of them, you know the proportion of black balls and white balls, right? But if you don't sample all of them, there's some uncertainty. Again, the hypergeometric distribution. However, that distribution is appropriate for the count of, say, black balls. I need the variance, so the variance estimators exist for that count, but I need the variance estimator for the proportion, right? So it's different. And so I looked in all my books and I looked in online and I could not find a variance estimator for a hypergeometric proportion anywhere. So I go to Google, I go to ChatGPT. This is a small digression. I go to ChatGPT and I say, hey, give me the variance estimator in algebraic form for a hypergeometric proportion. Boom, there it is. It spits it right out, just like that. So I take it and I stick it into my computer and I compare it to a simulation I've written, and they're not the same. So I take my code and I give it back to ChatGPT and I say, your estimator and my code are not congruent. And in its typical sycophantic way, it says, wow, you're really thinking well about this. You're right, for X, Y, and Z, here's the corrected form. Turns out it's wrong. And I go back and forth with ChatGPT, wrong, 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 wrong. It's always wrong. Eventually it goes back to the first thing it told me. And so, okay, I'm gonna have to actually think. So I sat down and I worked it out. And then I go back to ChatGPT and I test it against my simulation with a high amount of replication, complete bullseye, dead on, so satisfying. So I go back to ChatGPT and I said, hey, remember that hypergeometric proportion variance estimator? I figured it out. You want to know what it is? It's like, oh yeah. And I said, too bad. So if I get hit by a Tomahawk missile, you all know why. Anyway, there's a theory here that I'm not going to get into now that I used to figure out that all I had to do was take the count of the existing variance estimator for hypergeometric count and just divide it by a little n squared, which is the number of draws. That's all you really got to do. And this is some of the underlying theory for the reason why. But we also have this among site and occasion uncertainty. So this is, again, on the left, is within a site, but we also have multiple sites and possibly occasions where we're going to estimate this. So the moments of linear combinations of random variables becomes useful here. This is an example where you had 9 space-time measures of pHOS. You simply add up all of the variances and all the two times all the pairwise covariances and divide that one over the number of things squared. And you can get to this across pHOS variance estimator. But this is for the non-weighted one. This is just the naive traditional pHOS. So for the weighted pHOS, this is different notation now. This is switching into matrix notation here. But this is simply how you calculate variance for a weighted mean, because that's really all we need. However, this will work out to give you a variance that once transformed into a confidence interval could potentially be negative if the pHOS is very low and uncertainty is high, and it could be greater than 1 if pHOS happens to be really high and uncertainty is also high. So there's some stuff that can be done to ensure that the confidence intervals don't violate basic assumptions of probability. So the paper also goes into just, a little teaser on some statistical power. So we've got different kinds of pHOS, or different values of pHOS within a population. So a beta distribution is well suited for this. Here's an example with where the parameters of the beta distribution are known. And we have just 5 draws from the distribution on the left. And then we estimate these parameters using frequentist techniques. And, in this case, it actually came out pretty good. This is a real example with 5 data points. And the estimates came out pretty dead on, actually. But if you look at the size of the confidence interval, it's gigantic. And then here's an example just of one draw. This is not a mean, but just one random realization of 50 pHOSs from that distribution. You again get a pretty good estimate, not too different, actually, but now the confidence intervals are super tight. And so this is just merely to illustrate different ways in which you can go about planning how many samples you might want given your tolerance for uncertainty. And there's an appendix that goes through and actually implements all of the ideas for those who don't want to code it up, all the math themselves. It exists in an appendix. All right, so I'm going to kind of wrap up this first paper. The naive pHOS is naive in the sense that it assumes panmixia. However, assortative mating is very common in space and time. We know that different fish of different sizes, which is related to their age, have different fecundities. It's a real thing. So let's start using it. The HSRG pointed out this fact. I should have credited them for first pointing out the ability to incorporate size-specific fecundities into pHOS. They came up with that first. I notice a lot of confusion in this world, and one of them is people want to try to say, well, we know that hatchery fish have reduced recruitment performance, so let's just downweight them. Well, that would double dip with the theory that Ford had developed. So don't try to downweight those hatchery fish by their fitness, because that is already what this Ford model is trying to do. The variance estimators now exist. 20 years under the ESA, it never existed. But not all risk is genetic, okay? So this has some limited applications. I would argue more applications than the naive pHOS, but look, the naive pHOS is useful if we're talking about just ecological competitive interactions, like in an estuary where all these fish eventually kind of do interact in a panmictic way. Then just the simple proportion that's not weighted by natural origin fish is perhaps what we actually want. And not all, but typically we're interested in this domestication selection, but not all of the genetic risk is due to domestication selection. So you can bring in an out of stock basin, and there's like an additional thing, an additional out of basin genetic effect that would not be captured by the model of a domestication selection alone. So important to keep that in mind. And again, there's just a lot of confusion in this world, but particularly around transgenerational effects. And I guess it's just important to point out that these pHOS recommendations are based on a long-term equilibrium, okay? So indeed, pHOS and pNOB might change every year because of management changes or just things that are beyond human control. So this does set up an opportunity to do dynamic management where you can have a long-term goal, but if, for example, the number of natural origin fish returning is very low, you could choose not to mine all of those fish out of nature and just let them breed, right? In nature. But this would set up a little bit of a genetic debt that would have to be repaid later, right? Because you want to take these natural origin fish and bring them into a hatchery to slow down the domestication selection there, but maybe you don't want to take those last fish, right? So there's a potential to do more adaptive management with these ideas. Okay, so here's an example of using uncertainty in pHOS, and actually in a lot of other things too, into a decision. So this is a Bayesian belief network written up in Netica software, which is free. These are often done to mimic professional opinion, and that's what this one does. So we have goal attainment on the right. This is a hatchery's goal, and the hatchery's goal is defined by two things: the risk to the wild population and the fishery quality. Okay, there are different types of hatcheries, those that supplement a fishery, and then those that also augment an existing natural population, kind of like a zoo almost, like where you're trying to get a demographic boost. So there's these differences matter. It's very important. But if we think about just a fishery supplementation hatchery, this fishery quality is a big part of what we're trying to achieve with the hatchery, right? But we also want to keep the wild risk low. So it's a case of trying to have literally like trying to have your cake and eat it too. So we've got to balance those two things. So you're not seeing how these variables are actually mathematically blended, but at a qualitative level, this is what just sets up the goal. If we trace back the wild risk, we see that it's determined by two things. One of them is just how many wild fish we have in nature, right? So this is the demographic risk. The other one is this genetic one that I've been harping on this whole time. And here we have a case where the wild genetic risk could be determined by two different kinds of selective forces. There's the weak one, which was parameterized by Ford in his original model, and then a strong one where I showed you where that whole triangle collapsed down in this little sliver. So if natural selection is strong, this risk to natural origin fish through domestication selection is different, and it's much stronger. We have this other little control variable where we can blend, how much belief we have in strong versus weak forms of natural selection. Anyway, here we've got pHOS, these bars indicating a distribution of beliefs about what the values could possibly be. And so anyway, here's a case where we can propagate the uncertainty in pHOS into the final decision about goal attainment, right? And so there's a possibility of kind of reverse engineering some of this so that we try to maximize goal attainment as much as possible. Thus, using uncertainty not only in pHOS, but really everything over here. I haven't described it all, and don't have the time for that, but we have uncertainty in pHOS, we have uncertainty in the strength of selection. And so here's how you can propagate that forward.
Question.
Yeah.
Are these, like those pHOS and pNob, are those basically the priors, what you're just describing there?
If you have no empirical data, then it would be like a prior. You could just set it up based on professional opinion on what you think it is based on whatever, right? But it's exactly like a prior where it could be from other literature, it could be from some other hatchery down the road or in other parts of the state where you think that the dynamics are sort of the same. The pNob one though, like there's really never any uncertainty in this. Like what that is if you're keeping books. And they always do. So this one really actually probably shouldn't have any uncertainty. This could represent a cross-year variability. But yeah, like all of this, you have to decide for yourself. If you have data for it, great. Then that can inform the values that you're centering on and the dispersion. And if you don't have that variable, if you don't have such data, then you can just make it up. Make it up sounds really bad, right? And a lot of Bayesians will take flack for being so cavalier like that. But I will point out that ignoring it doesn't make it go away, right? So if you want to get to something like this, you've got to say like, well, what do I think is important in this system? And even if you don't have data, if that's affecting your decision, right, you may as well write it down and be clear and transparent about what your beliefs are that are affecting your decision. Right? That's my personal philosophy on and why I'm an advocate for Bayesianism and some of this stuff. Yeah. I don't have much time, so I'm going to actually skip that. And I was go into the next paper here on how to integrate statistical evidence in people's values. This one I think is, yeah.
So thinking about your specific salmon example, would the idea be that they would be calculating pHOS at the population level and then be rolling that up to the SU, where those things would be?
Yeah, NOAA typically requires in HGMPs that it get reported at the population scale. So that is way like the level that they often measure and report it. So the idea here is to measure it at that kind of population scale of where the fish are actually breeding. So at a larger evolutionarily significant unit, which is comprised of multiple populations. I don't really know how, I think you could just have the individual point estimates for the constituent populations and their uncertainties, but I don't know how that, like a cross population variance gets used in their decisions. So that is an interesting meta, like level thought that this just tries to replace the existing pHOS, which is again calculated at the population level. But I don't honestly know how they kind of roll it all up at that ESU level.
I guess my next question is, assuming the Ford definition of pHOS, wouldn't that be conservative in a conservation context? Because you're trying in many ways to minimize that. So if you're assuming it's bigger than it really is, you're moving in a direction that you.
Yes, it is more conservative. Absolutely. The magnitude by which it's conservative is kind of in that blue and red figure in that lower triangle. Yeah. Yeah. So if you're, there's this good fish, bad fish thing out there. So if you like hatchery fish, yeah, the message here is people have been overestimating the risk and hence been possibly being a little too conservative. But I don't want to go into the politics of that because I don't have a dog in the fight, right? Like I just want to get the math right. Okay, so I want you to think about how we can integrate statistical uncertainty with human values in a mathematically rigorous decision-making framework. So, I mean, this is sort of what I was already talking about, but I'm going to get even more mathematical now and more abstract. So let's just assume that we've got some data, and so we can either get the likelihood profile or a Bayesian posterior of different states of nature. It would be population size, survival, right? You think of it, right? But we have some state of nature, its status is uncertain, there's data available to quantify it, right? This is status quo science. But what if we also have some utility function? So the human dimensions folks go out and figure out, well, how happy are we with different states of nature? So if they can quantify this function, then I want to be able to get at the thing on the right, which is a probability density of utility. Now it seems, so how do we get there? Right? It seems like we've got all the pieces in front of us. Probability density, state of nature, utility, state of nature. And this is, how do we get to probability density of utility, right? These two things are over on the left-hand side. So how do we get there? Well, it's the transformation of variables technique. So some stat theory is going to happen now. So if we imagine as simple as possible, so X is a random variable, and then we imagine a very simple transformation where we're just going to square X. Okay, that leads to Y. So U is our transformation function. It gets us our new value for Y. W is the inverse function. So if we start with y, how do we go back to x? Right? So if our original function is just squaring, the inverse function is the square root, right? That undoes the square and gets back to the original. Okay, so if what we want to ensure is that this area here in magenta is the same as this area in blue, because otherwise we're not talking about probability anymore, right? We need to, if we're going to randomly land somewhere in this range, we need to have that probability match the probability of landing in this blue thing as opposed to everything else. Okay, so that's stated right here that the probability of y between 5 and 10 on the y-axis must be equal to the probability of the inverse. So this is the square root of 5 and the square root of 10, right? Which is this. This is the square root of 5. I don't know what that number is. And the square root of 10. Okay. This has to be true. And so how do we do this? Well, this one is fairly simple. We can just integrate from the square root of 5 to the square root of 10 of our original variable, x squared. But the one on the left is more tricky. So we have to use the integration by substitution. We have this inverse function, which is the square root, and then we take the derivative of it. That's this. And then we have our original function, which is, I'm sorry, the inverse function, which is square root. And now the original function was to square it. Okay, so that's why you've got the square root of y squared. This is the f, and this is our inverse function w. But now we can integrate that one from 5 to 10. And so if we do this numerically, because it's easier, you can see that they both work out to the same number. Great, right? Because this is satisfies rules of probability. This has to be true in order to arrive at a probability density of utility. So this leads to the general formula of the transformation of variables technique. There's some stuff here with the absolute value I could talk about, but it doesn't really matter. Okay, so let's run through an example here. We've got a beta binomial belief. So we flip a coin 100 times under two scenarios. Under a treatment scenario, we get 50 heads, and under the control scenario, we get 40 heads. Okay, so we've got, we could do Fisher's exact test on these data and get a p-value of 0.1. Okay, so that's what most people do in science, and they would conclude that, don't do this treatment because there's no evidence that it worked. And the treatment might be costly, right? Like, if you're going to go do something to enhance a fishery, there's some work, even just fuel people hours or whatever. So don't do the costly treatment because there's no evidence, and I air quotes mean something here, no evidence that it doesn't work, okay? That's what I would call status quo decision-making with p-values. But if we know this utility function, and in this case, it's, this is the human dimensions research where they do stuff, and then we can fit a model to it and come up with these functions. And even though the treatment has this additional cost, so you can see it's always below the control. And if we were to quantify this, and then we run these two functions through the transformation of variables technique, we land at a gargantuan equation, which is the utility density function of these two things. And notice that the treatment is to the right of the control, meaning that we essentially reap more utility under the treatment than the control, even though it was not statistically significant and there is a cost associated with the treatment. Okay, so let me just summarize what and because we have this closed form solution, we can also calculate the expected utility. So we can visually look at this and see, yeah, we get more utility from the treatment scenario than the control. But we can do the math on it as well because we have this. And so you can actually calculate the number to show by how much. That's kind of neat.
So that's a multi-attribute utility. You've included a cost in there?
Yes.
Okay.
Yeah, sorry. It is in there. In some of the other slides, it'll be in there a little bit more explicitly, but here we're including the cost and over here we're not. I know you probably can't even read that, but this is C with a negative number for the cost. And then in the control, there's no cost being implemented for not doing the treatment. This will come back in a moment if I have time. All right, so let me just summarize. In a standard analysis, Fisher's exact test returns 0.1. So you might conclude, don't do this costly treatment because there's no evidence that it works. But under decision theory, with the exact same data, but also this utility function, we can calculate the expected utility and arrive at the exact opposite conclusion to do the treatment, even though it's costly and not statistically significant. Okay, so we can just kind of keep doing this with all kinds of probability density functions and all kinds of utility functions. This is a different utility function. It's a little bit, there's another parameter in here, so it's a little bit more flexible. And we can get out, like, do you just keep doing this stuff? So here's an example where we just draw two different groups, kind of like treatment and control, or two different scenarios. And under two different parameterizations of this, right? We don't know the truth about this, but we just see this data. And then we ask, are these two groups different? So we can do a likelihood ratio test. And again, by coincidence, we get a p-value of 0.1 here. But if we run it through the transformation of variables technique, and here's what's a little bit more obvious, if we integrate in this control situation, where we don't have a cost, we integrate from 0 to 1 and compare it to what happens where there is a cost. And we're going to integrate it from negative 0.2. So this is a scaled cost, right? Compared to the benefit. And so here, there's more like negative stuff happening here, but it still works out to be greater utility, expected utility under the statistically insignificant and costly treatment. Okay, so this to me is how we can get to mathematical rigor in blending. It's sort of, to me, ground zero of science and human dimensions, right? Sarah will know very well that this is extremely simplified and that we often have multiple objectives that we're trying to balance that can't really all be contained within a single utility function. I acknowledge that reality, but I was searching for what felt to me to be kind of the math ground zero on how to integrate science and humans. I think this is the last technical slide. This one is just, I'm going to go really high level so we have some time to chat. But here's one where we just have different magnitudes of uncertainty. Okay, they're centered the same. And we can get out and calculate the expected utility. And this says, do action 2 because expected utility is greater in this red than in blue. But if we just change that utility function slightly, everything else is the same. But you can't even visually see it, but they're not the same. You have to look really close. This looks like a big difference, but visually it's not. Anyway, in that scenario, now we're going to reverse the decision, and the data didn't change. The data differ only in the magnitude of the uncertainty. Okay, so in my original proposal, think of a case where uncertainty is used, right? Like different magnitudes of uncertainty would lead to different decisions. Well, here's one where you have two different magnitudes of uncertainty, and we're just changing how we're being risk averse a little bit, how we're valuing different states of nature. And that uncertainty emerges now. So it's like an interaction between the magnitude of uncertainty and human values. Let me quick time check. Yeah, 6 more minutes. So I had some concluding thoughts, but I think I'd rather just kind of stop. I know it's going to be abrupt, but I think that might be better for everyone than me just kind of getting up on a soapbox for a minute, which is what I would have done. So thank you for your time, and I look forward to hearing your thoughts. I think we have a few minutes. Yeah.
Thank you, Dr. Falcy. That was wonderful. Anyone online can put a question in the chat, but if there's anyone in person that'd like to ask another question, please feel free.
Sarah.
So I've just been thinking about this today, it turns out, so I just wanted to get your thoughts about this. We think so commonly about utility functions, but we often also are working from nonlinear value functions where that function is developed without thinking with respect to uncertainty, right? And going back to utility theory. So this all applies, right, for nonlinear value functions as well as utility functions.
Yeah, so make sure that I'm capturing the essence of the problem or question. So this is a utility function. Are you also asking about how, like over here, like, this is just looking at the expected utility, but maybe you are more concerned about this part right here, like this lower tenth than this lower tenth. Is this related or?
I'm just saying that, so we think of utility, right? And that the way we actually derive utility is explicitly by thinking about uncertainty, right? So you think about like using gambles to derive utility functions for decision makers. But oftentimes it's not, right? There is a distinction between a utility function and a nonlinear value function, where we just value things in a nonlinear way with respect to the, say, natural measure, whatever the state of nature is, right? And so I guess my point being that utility, the way we develop utility, we are explicitly thinking about uncertainty, but we can also just have nonlinear value, where we have a function that looks exactly the same, but it's about a nonlinear value function rather than a utility function.
Got it.
Stuff all
Yeah.
works the same, right?
Yes, in fact, I think in light of these definitions, that value function would probably work even better here because there's no incorporation of uncertainty in this at all. This is just state of nature changes regardless of the probability of these different states. If we have more and more abundance, how much extra good do we derive from that, right? So this is, there's no concept, it's completely walled off from probabilities here, right? So this is in fact, I think, probably better defined as a value function, because it's divorced from the probability part, right? So like, to me, it's more like risk involves the value or the utility, multiplied by the probability of that thing occurring, right? And so, anyway, risk is kind of baked into this thing over here, where we look at different probabilities of different outcomes. And well, it's actually the probabilities of different dollar amounts, right? Like you're playing a lottery with, you can buy a ticket and there's a probability distribution of how much you can get back out of it.
And I think of the distinction between a nonlinear value function and a nonlinear utility function is really the way in which we derive it. And that we derive a utility function by eliciting value under risk, right? So we're usually using things like gambles or whatever, those kinds of approaches. But I think functionally, they essentially work the same way, except that you do have this sort of meta uncertainty value, right? We derive the utility with respect to uncertainty.
Yeah.
And then we're talking about how do we use it in making a decision under uncertain states of nature. So anyway, yeah, I mean, my sense is it works the same way. But it is interesting to think about this kind of meta certainty that you sort of think about in this way. Yeah, sorry, it's just been something I've been thinking about today because it came up in something, so we were debating this.
Yeah, I mean, maybe we can chat later about whether uncertainty in these parameters is a way of getting at some of that, right? Because this is just assumed that this function is known perfectly.
Yeah.
And it's not, but I think you're getting at something deeper than kind of simple estimation problem here, right? And so, yeah. So it's an interesting consideration that I honestly have never thought about. Yeah.
Are you saying that like if the uncertainty in X changes, then that would affect the utility function?
in the way it's derived, yes, utility functions are often derived. The concept of utility is derivation of value under uncertainty. Yeah.
One question online. Jim Pinelli says, great talk. Any comments on risk aversion? More specifically, finding actions defined as risk prone, neutral, and averse.
Yeah, great question. This is something I'm still wrestling with, and I think Professor Converse and I are going to have a conversation after this, and I'm going to get the truth from her there. But and I was kind of already getting at some of these ideas, so let me just see if I can address this. So I'm saying here, like you do a decision. Maybe this other one is better. First one. Yeah, we calculate the expected utility and you do whatever maximizes expected utility. Okay, I think this is quite reasonable. But what if you are it almost seems like overthinking it, but what if you're more concerned about this right-hand tail than the left-hand tail, right? That you get really excited about, even though it's low probability, but you get really excited about this big payout here, more so than you're concerned about the relatively low payout over here, right? So this is,
Fishing.
yeah, but
Big fish. I don't care about small fish.
exactly, yeah. There's any number of reasons why you're going to have essentially a function that goes up with it, like, bigger fish, greater population size, better catch rates, less risk of extinction. So it's not entirely clear to me right now whether expected utility is always logical, right? Does it make sense to have different weightings for different outcomes, or is it already contained right here? And I kind of feel like it's already contained right here, right? So that if you really wanted this big payout, you just have a function that's even higher, right? And then you run through all this, and then you just look at the expected utility and you're done. Don't overthink this distribution, right? Yeah. Okay. Yeah.
I mean, in sort of marine fishery stock assessment management kind of things, where the outcome is you're trying to set a catch. What's always struck me is that we do assessments and you might do a fancy Bayesian assessment that gives you all the uncertainty, and then you put the median into your catch rule that gives you the catch for the next year.
Yeah.
You ignore all the uncertainty. So one of my students is looking at like, what if instead of putting the median, you put the like lower 20th percentile or something, and then as it got wider, you'd have less catch. It's narrow distribution and high.
Yeah, exactly. I mean, some of my soapboxing, actually I deleted one of them out, but it was like, we have the ability to simulate everything now. We don't need to ignore the things that we can't estimate. If they're still part of the decision, let's just simulate stuff. And you don't need to be able to do all the math either, right? Like all that math that I just did, you actually don't have to do it. There's a simulation version of all of this. I very much think that we should be using all of that uncertainty we work so hard to do by just building a hypothetical universe, right? This isn't that hard, especially now. I mean, you don't even have to be a coder anymore, right?
Glad to hear you say that, because that's what I was thinking through this. It's like, wow, I didn't bother to work out the math because it just
right. Yeah.
But it is nice to see the math work out. That's good.
Perfect place for a quantitative seminar. Full math.
Yeah.
It's your place.
Going back to your pHOS variance estimates, would you consider using an open dispersion parameter for these variances, or is this a context where that wouldn't apply?
I do think it probably does apply. It was not developed in the paper anywhere, and you didn't see it just now either. So it's a really good question, but it's also an empirical question. And so if you look and you see that depends on how you're sampling and how the fish are distributed, right? So if your sampling frame includes a bunch of places where hatchery origin fish just never go, your pHOS is not going to be beta distributed, right? There's going to be a bunch of zeros or ones in your data, and so that beta distribution just won't make sense. And then, but I still think the variance estimator would still work though. But the beta distribution is maybe not necessarily the right distribution. So I kind of had a few things on the screen there. Variance estimators, which I think would be robust even under scenarios where you have zero inflation. But that beta distribution does not account for, well, it doesn't account nicely for zero inflation, and so some over dispersion might be needed there. I have to think about that a little bit more, but I'm pretty sure that the variance estimators would still apply if you've got a lot of zeros and ones. Yeah.
Well, thank you everyone so much for coming. Thank you for that wonderful presentation, Dr. Falcy.
See you guys next week.
That's it.
Eric, can I just come by your office at 3:30 or so?
Yes.
We'll
Yeah.
grab Mark or.
And Mark.